We've explored the sine and the cos, okay? And we did different angles and the sums of them. And we didn't do tangent, but if we look back to here, these are the identities that we've been exploring, and were verified in the many different examples here. Okay. Now, very similar to the sum identities are the difference identities. Okay, the difference identities. We won't go through the same activity where we try to verify all of these, right? We won't go through that same activity. But, as you can see, they're very, very similar. Look at the sign, okay? If we have an angle that can be added up, you know, that two angles can add up to that angle, we have a sum identity. And notice for sine, it's sum and sum. It's difference and difference. For the cos, it's always opposite, okay? So if you're memorizing this, you don't want to refer back to this all the time. Those are some good things to memorize. So they're very similar. We didn't talk about the tan, so let's talk about the tan. Let's test the tan together. Okay, so tan. Let's do a difference, and we'll test that tan. Let's make some space here. Okay, a difference. So let's all do this one here. Let's do tan of 70. Okay, let's do tan of 70 degrees. And so that tan of 70 degrees is actually going to be, let's think of a difference. Let's think of two angles that when you subtract them, you get 70. Anybody? Sorry? 90 and 20. Okay. Okay, why would I hesitate with that? Why would I hesitate with 90 and 20? Because tan of 90. Okay. All right. There was enough of you. Okay, so tangent of 90 is 1 divided by 0. Okay, we got a bit of a problem. Does that mean this identity is total hooey? No. You ever heard that word before? Hooey? It means like garbage. Like, yeah, hooey. Other things. But does it mean that identity is wrong? No, it doesn't. Okay, that's different than a counterexample. Okay, that's different than a counterexample. If I say to you that 1 plus 1 is 2, and you say to me, Mr. Maxwell, that is not true because I can think of two numbers that makes that not true. I was like, okay, what is it? 1 plus infinity. 1 plus infinity. Okay. Well, what is that on your calculator when you calculate that out? Well, it's not possible. Well, if you think of an example that is not possible to actually evaluate, that doesn't make it a counterexample. 1 plus 0 works. Okay, but if you involve infinity in some kind of verification, mathematical verification, you got problems, right? So that's a very good point to ask if that's a counterexample. Not a counterexample, but it is still something that you need to be aware of. So we don't want to use an undefined value here in testing this. So I'm glad you said that, actually. So don't feel bad. I'm glad you said that because it gave us that teaching point there. So what's another one? Ones that we'll be able to evaluate. So we don't want to use 90, but let's use 100, which would make this 30. Okay, so let's do that. So just to test that, so we'll get our calculators out, of course, and we're looking at this identity down here. And so I need to do tan of 100, because that's A is 100. So tan of 100 minus tan of 30. That goes in the numerator. So tan of 100 degrees. And tan of 30. Okay. And then on the bottom, it's 1 plus the product of those two. So 1 plus tan 100 times tan 30. And notice they don't use brackets a lot when using trig, like if they're multiplying two things. They don't use brackets. You don't need to. You can kind of distinguish where the tan function ends, right? Because another one begins. If I said 54 and I said, no, that's 5 times 4, you'd say, Mr. Maxwell, you have to do more than that because that looks like the number 54. If you want it times, you got to do this. They don't do that with the tan functions because you can see where the tan ends, right? It ends here. We start another trig function, so they don't use brackets. Okay. So many of you have started this already. That's great. But what is tan of 100? Shout it out. Tan of 100 is? Doesn't exist? No? Tan of 100 is? Okay. Is that verified? You guys, anybody else get that? No? Yes? No? Okay. Let's test it. Let's go to the all-knowing calculator on my screen. Okay, are we in degrees? Okay, I'm not in degrees. I got to go down to degrees. Make sure your calculator's in degrees because we are looking at 100 degrees. Okay, and we'll put that, go back to the screen. So tan of 100 is negative 5.67128. Did anybody else get that? This one? Yeah? Was your calculator in radians perhaps? No? Okay. It's just being not nice to you today. Tan of 100. That was tan of 70. Oh, okay. All right. Yeah, we could have done that first too. But let's do this one. Tan of 100 is negative 5.67128. Okay. Negative 5.67128. Okay. And let's do tan of 30. Okay, so what's tan of 30, anybody? Sorry, 1.5? 0.5775? 35? Okay, is that good with that? All right, good, good. And then 1 plus. Okay, now we got to multiply these two together, I guess. Right? So 1 plus. Now this is going to be a negative. Looks like. This was positive, right, Danny? 0.5. That was positive. Yeah. Okay. So what's the product of those two? Oops, don't want that. The product of those two would be, so that number times, you said, 0.57735. Okay. Is going to be negative 3.27. Yes? Okay. Negative 3.27. What was that? 43. Okay. All right. This is pretty complicated. Let's see if this works out. So when we subtract these, what do we get on top there? Anybody done this yet? Sorry, negative 6.24863. Okay, agreed? Yes? Somebody else got that? Okay, what about over here on the bottom? So 1 plus or minus this. So that's going to be what? Negative 2.2743. Correct. Okay, 27. Okay. And so when we, what did you say this one was? Tan of 70 over here? 2.7474. Okay. 7474. Oh, 77. Yeah. Okay, thanks. All right. Okay, so what do we get when we divide this? We done that? So we get the same number. Okay, let's check it out real quick here. 6.24863 divided by negative 2.2743. And there we go. We get the same number, positive. Okay? Okay, so those are equal. That's great. Now, I know you're thinking. You're thinking, why do we spend all that time testing all of these numbers? The reality is that there are a lot of things in math that I tell you are true, and you don't actually spend the time to verify it. And so, because these are identities, because these are pretty important, I just wanted to spend a little bit of time showing you that, hey, when you actually do this and test it out in multiple different angles and all that sort of stuff, it does end up to be true. So we tested those two. We also tested this one, and they're true for the ones that we tested. Okay. I do need to finish up this lesson here, so I do want to talk to you about the double angles, and I'm not going to verify this like we did, but the double angle identities. Okay, a little bit different, although much the same. If we're talking about double angle identities, okay, the pattern is, and here's the sign of 2 times some angle. So it's this angle that we're actually going to be writing the sort of the explanation with, okay, this angle A. And this is the identity here. 2 sine A times cos A. And so if we're looking at this and we say sine of 60, let's say, well, in the double angle formula, and obviously you could write this as sine of 30 plus 30, but here we're saying we could also write this in a little bit different way, where it's sine of 2 times 30. So we can use the angle 30 here and here. So let's just take a look at this. Sine of 30 times cos of 30. Okay? And that's what they're proposing is true. And of course, we'll use these numbers because they're a little bit easier to work with, right? So sine of 60 is root 3 over 2. Okay. Root 3 over 2. And sine of 30, okay, sine of 30 is 1/2, and the cos of 30 is root 3 over 2. Okay. Is 1/2 here. Cos of 30, root 3 over 2. Well, if you look at this, it's pretty easy to say here that 2 times 1/2 is 1, right? And so we have root 3 over 2 equaling 1 times root 3 over 2. Okay, so there's quickly, just a quick verification for the one double angle formula. All right, and if we look down here, okay, and in your textbook there, we see that there are, that's the one double angle formula. There are several for cos, actually, and there are several for cos, and each of these are written a little bit different. This involves cos and sine. This involves just cos, and this involves just sine. Okay, and I'm going to show you, as sort of the last point in this lesson, I'm going to show you why these work, why these are true. Okay, so it's a little bit of a, this is sort of like proving or changing one expression into another using other identities, and that's kind of the goal of this whole chapter. So we'll just talk about those. That's not your assignment for today, by the way. I've changed it because I knew it's short in classes. So, yeah, if you look at example 2 in your textbook there, okay, so it's this. Example 2 says, determine an identity for cos of 2a that contains only the cosine ratio. So you're given this, cos of 2a equals cos squared a minus sine squared a. Okay, so this is one of the identities, right here, the first one, up here. One of the identities for cos, double angle identity for cos. And it says, write it in such a way that only contains the cosine ratio. So what we're going to look at here is this. We're going to say, I want to write this with only cosine. Okay, there's cosine. Oh, there's sine. So how can I rewrite sine squared a in terms of cos? And this is where we're starting to look back and say, I want to focus on this. What's a different way that I could write this? And if we go all the way back, to yesterday's lesson, all right, look at what we did here. From this Pythagorean identity, we could actually move these around a little bit, and I could actually write cos in terms of sine, and I could also write sine squared in terms of cos. So, whoops, went too far. Sorry. All right, right here. So because we have this, and you don't have to write this, just watch. Cos squared a plus sine squared a equals 1. I could actually write sine squared a as